I'm excited to introduce Matteo Tarocchi from University of Milano, sorry, who will be talking about Thompson-like groups acting on fractals.
Thank you. And thank you all of the organizers for the opportunity here, because it really feels surreal to be speaking right after you and for the so thank you all. And all right, so I'm going to be talking about Thompson groups here, and then to introduce a generalization of them, which are called rearrangement groups. Essentially, Thompson groups are it's a trio of groups, very famous F, T, and V, and they act on the unit line, unit interval, the unit circle, and the Cantor set, respectively. Whereas rearrangement groups can actually act on different spaces, called limit spaces of replacement systems. This is one example. So they can be fractals, but they can also be just lines. Okay. And I will just start with Thompson groups. So if anyone doesn't know them, I don't think you'll be lost. So in order to define each of these three Thompson groups, I'm going to give you an idea of how to essentially subdivide something. In this case, we start with just the unit interval, and I say that dyadic subdivision of the unit interval is a partition that you can obtain by just cutting things in half. So for example, you can cut in half the interval just in one way, just this way. And you can then cut each of these halves in half, and you can go on like this, etc. If you stop after finally many halvings, you've got a dyadic subdivision. And the good thing here is that you can actually represent the same thing with trees. So if you start with the root here, which essentially represents the entire interval, you can go down and split in two each time you are making a dyadic subdivision. So here I mean that I'm literally splitting the interval in half, and then I can, for example, split in half the right half and the left half. But as you can see on the left, essentially the second half of the first half has been split. So this is a more accurate picture. This is totally equivalent to the dyadic subdivision on the left, and you can probably see it, like if you follow. This dyadic interval is this leaf. And for example, this dyadic interval is this leaf, and so on. So you can actually read the dyadic intervals of these dyadic subdivisions on the leaves of a dyadic tree. And this will be very useful and will be later generalized with rearrangement groups. So the elements of Thompson groups that we are interested in are called dyadic rearrangements. And these are defined as the homomorphism of the unit interval itself that are piecewise linear, that preserve orientation, which basically means that they fix 0 and 1, and that map linearly between the dyadic intervals of two dyadic subdivisions. So for example, we've got the plot of nice graph here. We will not be using this kind of representation of elements because it mostly just works with F and kind of T, but it doesn't really work with the arrangement groups. So yeah, it's good to have it here, but we will not see anything like this later. Instead, we will like this kind of representations, which are essentially just pairs of dyadic subdivisions. And here we mean, for example, that the first dyadic interval 0, 1, 4 is mapped linearly to the first dyadic interval of the second subdivision. And the second goes to the second, the third goes to the third. You just go in order. And you can see the same thing happening in the plot, of course. And if we want to use trees, we can do the same with these kind of pictures. These are called tree-pair diagrams, and they're essentially just pairs of dyadic trees with the same number of leaves. And again, we go in order, and you can actually see that this is a permutation of the leaves, but it's a very simple one because if you count them, you are just going in order. This will change with Thompson groups T and V, but for now we are just going in order like this. All right, so Thompson group F is the group of these kind of elements, and it's got many properties. I just listed a few here. First of all, this is clear, but you never know. This is infinite. It's an infinite group. We are dealing with infinite groups in this context. And it is actually F infinite. It's got all the finite properties that you want. And this is a sentence that you will hear a lot here. We've got that the commutator subgroup is simple. we will hear of this a lot. And also, we know that F does not contain any non-abelian free group, which is linked to the following question. This is a very important question, open for like decades. So if you've never heard about Thompson groups, I think you might have at least heard of this open question about F. We still don't know whether it is amenable or not. And this group has been introduced like 50 years ago, and we still don't know about this. We don't even know what should be true here. Like, it's not just that we are lacking the proof. We literally don't know what to prove here. And yeah, so you might have heard about Thompson group F for this reason. And about the other two Thompson groups, we've got the second one called Thompson group T, which is defined in the same way essentially, but instead of unit interval, we will be dealing with the unit circle here. So each time I have 0, 1, I'm going to have S1, which you can just think of course, the unit interval after you pasted together the two extremes. So dyadic subdivisions are exactly the same thing. You've got 0, which is kind of fixed here, and then you can cut in half, another cut, another cut, another cut. You stop whenever you want, and this is a dyadic subdivision. It's exactly the same thing. You can also represent these with trees in the same exact way. The distinction here is that if you want to represent these with pairs of dyadic subdivisions, you need some sort of color. Because if this picture were black and white, then it would not be clear where anything would go. For example, I got that the red dyadic interval here is being mapped to the red dyadic interval in the range, but without colors, this would totally not be clear. And in truth, we only need one color, because once you fix the red color here, everything goes in cyclic order. And this is the essential distinction between Thompson group F, T, and V. You can permute these dyadic intervals in a cyclic way in this case. And you can do the same with trees. So this is a tree-pair diagram for the same element, but we are lacking colors, as I said. So we can essentially fill them in the same way, like I say that this is the red one, and this is the red one. This is actually sufficient, because you can then go in cyclic order. I mean, if you fix the red one, it's the first one, and then you go in order, like 1, 2, 3, and 4 is back there. And this is the permutation on the leaves. All right, so this is the distinction between F and T. And it's actually got some similar properties and also some quite different properties from F. It is an infinite group. It actually contains like infinitely many copies of Thompson group F. It also is F infinite, and it itself is its own commutator subgroup. So this is quite different from F. It is simple and the same as its commutator subgroup though. So if I tell you that the commutator subgroup is simple, I mean, that is kind of silly to say, but it is true. And as I said, this kind of assertion will be very common here. Also, it contains non-abelian free groups, so there is no problem here. We know that this is non-amenable. And just to give you an idea of how big this group is, it contains every finite cyclic group. And about the last, about the last of Thompson groups, I think Rachel will also introduce V and probably tell you a lot more about it. I will not give you the full definition here, but essentially you can think of V as being the group of these kind of diagrams. You take two times, the unit interval, and you cut in half, as you did with F. But the difference is instead of cutting, having the middle point being where the two halves attach, you are going to take two separate intervals. So there is nothing here in the middle. And then you can do this again, for example, like this. We do it for this. And then you can essentially permute these intervals in any way that you want. So for example, I can color this by blue. This guy is going to be blue. This by red. And yeah, you get the point. I can do any permutation that I want. And of course, I can do the same with trees. I'm not going to color the leaves of these trees because it's literally the same thing as we did before. But what's important is that now you need every color, otherwise this permutation is not clearly defined. So I should need to actually color every leaf of these two trees. And yeah, just to conclude about this, Thompson group F needed to preserve this linear order, Thompson group T needed to preserve the cyclic order, and this does not need to preserve anything at all.
Is this one known to be amiable or unamiable?
I'll get there, but no, this is not. Yeah. It's a good question. I mean, it's open for F, so why shouldn't it be open for V? But it is not amenable because this group is even bigger than Thompson group T. Indeed, I think you can tell it contains copies of T. You just take the cyclic permutations. And since T contains nonlinear free groups, V also does. So this is not amenable. It's got essentially very similar properties to those of T and many more. So essentially, even it is the same as its commutator subgroup, which is simple. And just to give you an idea of one distinction between T and V, V contains every finite group, not just every finite cyclic group, which I think you can see why. You can literally build any permutation inside here, any permutation group, because you take dyadic subdivision in n intervals, if you unit them, and that's Sn. That's the symmetric group on n elements. All right. I think this is enough with Thompson groups, and I am now going to introduce replacement systems, which is essentially, okay, recall how I actually defined some way to subdivide the interval of the circle or whatever happened for E. Okay, I'm going to essentially define a very similar thing. You start from a base object and you subdivide it in some way, and then you will get your group. So these kind of objects were introduced very recently in 2019 by Jimmy Belk and Brady Forrest. So we don't know that much about them, as you'll see. These are fairly recent. Belk and Forrest actually define these groups as a generalization of both Thompson groups and the Basilica Thompson group, which I'm going to define here as a rearrangement group, but this was actually defined in a slightly different way earlier, like in 2015, if I'm not mistaken. And yeah, the idea here is that our replacement system is a triple of three sets, essentially. Two sets and one graph. As you see, the first thing is just a finite set of colors, which can easily be just a singleton, and you will get just non-colored graphs. But anyway, if this is not singleton, you will be dealing with edge-colored graphs. Each graph that I'm going to be talking about is going to be colored by this. There is a finite graph, which I will call the base graph. And this is where we essentially start subdividing things. And then we got a set, which I call R for replacement, which consists of one graph for each color. And these are called replacement graphs. Each of these graphs is equipped with an initial vertex and a terminal vertex, just to make sure that you understand how to glue things together when you go and replace. So the idea is that you start from the base graph, gamma, you choose your least favorite edge that you want to see gone, and you just replace it with the right replacement graph. And with right, I mean, for example, if you are replacing a blue edge, you use the blue replacement graph. So there is a different rule essentially for each color. And now I think you understand that if I choose every edge of the base graph and I replace it, and then if I get a new graph, and then if I choose each edge of the new graph, I get another graph, and I can go on and replace everything furiously, infinitely many times. This gives a sequence of graphs whose limit is essentially what we call the limit space. I know that this is vague, but the full definition is a little more involved. But I think you'll be convinced once you actually see an example. So this is the Basilica replacement system. This actually gives the Basilica Thompson group as a rearrangement group. As you can see, the base graph consists of just 4 edges, 2 of which are loops, and the replacement graph is only one because we've only got the black color here. So the idea is we choose our least favorite edge, like the one on top, and I replace this, which essentially consists of cutting it in half and putting a loop in the middle. And we can do this with any edge. So I think you can believe me if I tell you that, for example, if I replace this loop, there is a new smaller loop, it's smaller just either way it's drawn, and 2 new edges. And you can do this with edges that have been just discovered, just generated by another replacement. and you can go on like this. And I think you can see that if I replace everything, you get a lot of these loops essentially. And so you should probably believe me if I tell you that this is the shape of the limit space. All right. This is called the Basilica limit space. It's actually homomorphic to a Julia set, the Basilica Julia set. And by the way, now that we are here, limit spaces are very well-behaved spaces. I mean, these are topological spaces that are like Hausdorff, paracompact, and they're metric spaces. So they're very good. You can actually define the metric, a metric. They are all equivalent if you do it like this, by just describing the lengths of edges of the base graph and the replacement graphs with certain hypotheses that are honestly not too hard to graph. But anyway, just know that these are very good spaces. And you can actually do the same with forests. As you saw for Thompson groups, we had trees, now we just have forests. The reason for the distinction is actually simply that for Thompson groups, we started with one edge or one loop, like the circle is kind of one loop, unit interval is one edge. In this case, we might just have more edges. So it's not really a big distinction. The main distinction is probably that we are going to need labels here. So if you remember what the base graph was here, it's this guy here. I'm going to call these edges R for right, L for left. And you can probably see that this RL is actually representing this edge from right to left. LL is the loop from L to L, and so on. So if you read the leaves of this right now, a very silly forest, it's actually telling you what the graph is. You can totally forget about the graph right now because it's all contained in here. And you can also forget about the replacement graph because you can write it as a tree. I actually wrote replacement forest, but this should probably be a tree. And the idea here is that if you decide to expand, let's say, this edge, this is what's going to happen, and you've got a new vertex that I'm going to call X, and you can call it whatever you want. What's happening in the forest is that you choose the edge that you are replacing, which is RL, and you attach these three below it. And then for the labels, you need to check the letters in the replacement forest. I and T stand for initial and terminal, which are in this case R and L, whereas X is this new letter that you've seen here, for example. Now, there is something very important to be said about X, but first, this is the same as this expansion. This forest encodes the exact same information of the expansion of the base graph. And one thing, if you want to, for example, expand this guy here, the initial vertices are going to be X. Initial and terminal are going to be the same, X and X. But we cannot use the letter X now. We need to use a new letter, of course. This is, I mean, if you replace these, there is a new vertex. You need a new name, like Y, for example. And this is very important. So you need to put new letters here. So essentially, you should think of these letters, every letter in the replacement forest is different from I and T, as free variables. You are going to need new letters here each time you do one expansion. All right, so this is equivalent to what we did earlier, and I'm going to be faster here because you've already seen a replacement system, but this is another one which has been studied, and it's probably a little trickier because it's got two colors, just for that. The idea here is just that if you replace the blue edges, you are going to essentially cut your blue edge in half, and there is going to be a red circle made of two red edges in the middle. And if you replace a red edge, again, you cut it in half, and there is a blue edge coming out of it in the middle. So, by the way, since we are always cutting things in half, I think you can also see where Thompson groups kind of come into, right? You can actually see that this thing is kind of like a Thompson group F on this horizontal line and a Thompson group T on this circle, but yeah, more on that later maybe. Right now, I think you believe me if I tell you that the limit space of this, which essentially can be built by creating all of these circles and making all these blue lines appear to all circles, is this shape that you saw at the beginning. And yeah, this is another limit space. This is actually homomorphic to another Julia set. Not all limit spaces are Julia sets, once again, but these two are. And yeah, okay, the same thing can be done. Even here, I will keep expanding this because it's the same thing. Just know that we can do all of this with forests. And this time, if you want to, for example, expand a blue edge, you need to put this forest with 4 branches. If you want to expand a red edge, you need to attach a forest with 3 branches with the right labels. Essentially, we've got 2 different rules, but you can decide which route to use by the color of the label. Now, we are finally ready to essentially define our elements of our groups, which are called rearrangements. Here, as we did with Thompson group F, we fix a way to replace things and to subdivide things. So we fix a replacement system. We, of course, fix its limit space, and then we define the elements in this way. We say that a graph pair diagram is just a graph isomorphism between 2 expansions of the base graph. Where by expansions, I don't think I told you, I just mean the base graph after I, of course, replaced a few edges finally many times, which is the same as dyadic subdivisions, right? You take your main object and then you subdivide it finally many times and you're done. You take 2 of them and you take some sort of isomorphism between them. It's the same thing. And in this case, our rearrangement, the actual element of our groups are going to be homeomorphism of the limit space induced somehow by these diagrams. What do I mean? Well, if this is a graph pair diagram, where I am using colors in a kind of an improper way, here I mean that the blue guy on the left is being mapped to the blue guy on the right. These are not the same colors that I meant before. These colors are useful because they allow me to show you that this is the actual rearrangement. So I am showing you above a graph pair diagram, which is just a graph isomorphism, but I am really implying a homeomorphism of the entire limit space here. And I think this is pretty neat. You can encode these things with finite things. And also, this is a blue edge. I mean, it's blue just because I colored it blue. It's actually an edge of the only color here, but this edge corresponds to a subset of the limit space, which is called a cell. Each time you've got an edge, it corresponds to some part of the limit space, a subset of the limit space that is going to be called a cell. And these are actually very important. These are kind of like the building bricks with which you build the entire limit space, the self-similar pieces that make this up. And beware that here, for example, I've got 2 edges, 2 red edges, because using different colors would have been a mess. So you've got 2 different cells. So on top and cell in the bottom. And the same for green. Okay, now you can do the same with forests as you probably imagine. So I can just draw the 2 forests representation for these expansions. And you should put labels here, which I think is useful to do once, because if you decide that this is LX, of course you can decide whatever you want here. But what's important is that you put the right labels in the range here. I could say that this is R, this is L, but I don't like this. I'm going to essentially name things in the same way in which I used colors with Thompson groups, where I said that the blue guy goes to the blue guy. Here I'm saying that R is going to be mapped to R. So this is going to be L. Essentially, I'm naming based on the pre-image of these vertices. And then if I put the labels in, what's good about this is that I can essentially recognize where everything is being mapped in the following way. So, for example, this is LX. The fact that this is LX tells you that if this leaf is going to be mapped to this leaf, and so on with the other labels, which I'm not going to fill in, but it's the same way as before. So you can completely forget about graph pair diagrams here. If you want, you can use these forest pair diagrams. Everything is in the leaves, and you can just read the permutation on the labels. Okay, so these are a few properties that have been studied about these 2 latest rearrangement groups that I just introduced. Not many rearrangement groups have actually been studied very deeply. Like there is also the big check fractal rearrangement group that has not really been studied that much. And yeah, of course, FT and VR rearrangement groups, but I'm not including them here. They've already been studied in many other ways. So TB and TA are the basilica and Herculean rearrangement groups. Belk and Forrest in 2015, as I anticipated, studied TB, and I studied TA in similar manners in my master's thesis. And there are very similar tasks. So these are all finally generated. TB is by 4 elements, maybe less, but we've got a set of 4 elements. TA is generated by 5 elements, and actually 4 of these 5 generate a copy of TB. So TA contains TB in a very natural way. And also, I really like the TA is generated by a copy of Thompson group T and a copy of Thompson group F. These 5 generators are like 2 for F and 3 for T. I don't know, maybe it's just me, but I really like finding this out. And yeah, anyway, the commutator subgroup, we know a lot about them. We know that they are finely generated. We have some explicit generating sets for them. We know that they're simple, and I'm going to tell you something about them later, but yeah, once again, this has come up again. And we also know that, and there is a distinction here, the commutator subgroup of TB has finite index. It's index 2, and I think I'm going to convince you why in a few seconds. We instead know that it's infinite, the index of the commutator subgroup, I mean, in TA. And so we can say that TB is virtually simple, whereas TA is not, for example. Now, about these commutators. For TB, we have this nice picture, which can actually help you understand when an element belongs to the commutator subgroup. If you take a rearrangement, any graph-pair diagram for a rearrangement, you can immediately tell if it's an element of the commutator, but just seeing if it preserves this coloration. So if it maps any yellow component, essentially, any yellow region of space to a blue one, it's not in the commutator. And this doesn't only look pretty. I mean, it's also, it should tell you how much we know about these commutator subgroups. And this is probably part of the reason why we were able to tell that they are simple in a fairly kind of almost easy way, as you'll see. There is a very similar characterization for TA, for the commutator subgroup of TA, but it is a little more involved. It essentially consists of studying the extremes of the airplane. Like if you take the figure, the base figure of the airplane, you've got extremes here, and each time you've got a new, essentially, ray coming out of a circle, you've got a new extreme. So it's a little more involved. You need to see how all of these extremes are kind of dilated or shrinked, and you're essentially studying some sort of derivative to the extremes. So it's a little more involved, but what's important is that for TA, we also have a fairly simple way to actually say if an element belongs to this subgroup or not. And this is why we were able to prove the simplicity here. We actually used 2 sort of ingredients. The first one is the so-called double commutator trick by Epstein. And if you don't see any double commutator, that is because the trick is working. So yeah, these things, this tells us that if we've got a normal subgroup inside the commutator subgroup, and normal subgroup is not trivial, then this normal subgroup must contain a lot of commutators. And by a lot, more precisely, I mean every commutator of G and H, wherever G and H are elements of the commutator subgroup which are supported on the same I, which is a subset, a proper subset of the limit space. Alone, this does not tell us much, but if you choose the right set I, you can then conjugate this identity by any element of the commutator. And since n is normal in the commutator subgroup, this essentially realizes the same identity as before, with the difference that we got T of I here, not just I. And we know that a lot of elements are in the commutator subgroup. So we are able to actually pick the right I, to pick a properly chosen K, and to map this K of I in a very big subset of the limit space. So we are really taking a lot of commutators and saying they all belong to N. And this is kind of the second ingredient. We know a lot about these commutator subgroups, and we know where to map K of I. And the most important thing is we know the generators of these commutator subgroups. So just by hand, we were kind of able to show that the generators belong to the commutator subgroups. And I think that the end of the story is kind of that we were able to do this because we know that much. This is, at least in my opinion, not very easy to generalize. I mean, the first step, yeah, of course, but the second step here, I would not know how to do this. Yeah, it's still weird that there are all of these commutator subgroups that are simple. So there must be something else here. And now, these are, let's forget about TA and TB for a few seconds, a few minutes. These are results about the commutator subgroups, the rearrangement groups in general. And there are not many because we don't know that many things right now. The first two results here are due to Belk and Forrest in their paper in which they introduced these groups. They also prove that any rearrangement group acts properly and by isometries on a Katsiri cubical complex. This complex is essentially given by a groupoid of rearrangement in which you are changing the base graph. So it's a generalized rearrangement. You don't necessarily have the same base graph in the domain in the range. And the second thing that Belk and Forrest prove here is that we've got a sufficient condition for a rearrangement group to be F infinite. I am not going to state this sufficient condition because it's not very fast, and easy to tell, but you can find it in the paper. It's essentially, you need a bound on the vertices of the expansions, and then something else that has to do with reductions instead of expansions, which is not very easy to verify, actually. And it didn't work for TA and TB, for example. Actually, we know that TB is not even finally presented, so of course it doesn't work. But yeah, it's good that we know of a sufficient condition, but right now this is not very easy to check. And one last thing that actually me and Davide Perego proved very recently is that if a rearrangement group is very transitive, whatever that means, then it is not invariably generated. Now, what do I mean with these two things? Well, first of all, we say that a group is invariably generated when it admits a generating set S that is invariant under conjugation, by which I mean that if you take the elements and you conjugate them by any element that you want, you still end up with a generating set. And Thompson groups have been studied under these aspects. So we know that thanks to a paper by Donald and Shchenko of 2016, we know that Thompson group is invariably generated. Is invariably generated. I didn't want to cut IG in half. And we actually know of a generating set of 3 elements that invariably generate. They actually proved this by hand. I mean, the proof was specifically tailored towards F. So we didn't find this to be generalizable in any way. Instead, we noticed that the proof for Thompson group TMV being not invariably generated, this had more to do with dynamics and could probably be generalized. So the first thing that we did is we found a way to separate these two things, these two contexts. And we ended up with this definition. So we say that a rearrangement group is weakly cell-transitive if it can map a proper union of finely many cells inside any cell that you want. Now, remember that a cell is the equivalent of an edge from an expansion of a base graph, the base graph. So these are the building blocks. These are a lot of sets that are interesting are actually union of finely many cells. And this definition is actually more natural than it might sound because we found out that in this context of rearrangement group, it is actually equivalent to other transitive properties that we find in literature. For example, this is the same as saying that the group is flexible, which is another transitive property that essentially tells you that if you've got two closed sets whose interior is disjoint, you can map one inside the other. These are equivalent in this context. And also compact open transitive is equivalent to this, which is another transitive property. So it is more natural than it sounds, and it actually implies that the action is minimal, which means that, for example, that the orbits are, the pointwise orbits are dense. Now, first of all, this definition works in the way that we wanted. Thompson group F is not weakly cell-transitive, whereas Thompson groups T and V are weakly cell-transitive. So we managed to actually separate these two situations. And we also found out that TA and TB are weakly cell-transitive. As I said, we know a lot about the commutator subgroups, which are very, very transitive. So of course, the groups themselves are. Also, I briefly mentioned the Witcher fractal. The Witcher rearrangement group is also weakly cell-transitive. Right now, we don't know that many rearrangement groups that are not weakly cell-transitive. We can think of a few, but all of those that we can think of are actually kind of like products of smaller rearrangement groups. You can kind of subdivide them in pieces, and so they're not weakly cell-transitive because they are on a few orbits somehow. Yeah, anyway, what we proved about these is that if a rearrangement group is weakly cell-transitive, then it is not invariably generated. We use the same ideas of Golan, Gelander, and Terschenko and just generalize their ideas. So the steps of the proof, which I'm briefly going to mention here later, are essentially the same. And it follows that, for example, TB and TA are not invariably generated, but in truth, we actually proved a little more than this. But I think you understand why I didn't put this as the main statement. I'm going to try to read this. Okay. If I have a non-trivial normal subgroup of a weakly cell-transitive subgroup of a rearrangement group, then this normal subgroup is not invariably generated, which is a lot less elegant than the previous statement, but it is true. And so this actually applies to the commutator subgroups as well, for example. Now, the idea of the proof, which, as I said, is the same of the paper from 2016 by Golan, Gelander, and Terschenko, is the following. It's mostly about dynamics. So the first is a definition of dynamic. This can actually be found in dynamic systems, in the study of many dynamic constraints here. You define a subset of the limit space as being weakly wandering for an element G if for every integer power of the element G, either this element of this integer power is trivial on A, or it's actually mapping it to somewhere else. So to somewhere else, I mean this part here. Now, the first thing that we prove is this lemma. Every element admits not only a weakly wandering subset of the limit space, but a cell that is weakly wandering. Then we prove, thanks to the weak cell transitivity, that if you've got an element G and a union of finely many cells, up to conjugating that element, you can say that that union of finely many cells is wandering for that element. So you can actually pick any union of finely many cells that you want that will be wandering for some conjugate. And the last step, which I think is, it's a fairly standard argument for proving that a group is not invariably generated. It's saying that a subgroup, a specific subgroup generated by an element for each conjugacy class is not the entire group, because this is an equivalent definition of invariable generation, saying that every subgroup that is generated that contains an element for each conjugacy class is the entire G, or saying that a proper subgroup cannot intersect every conjugacy class. So in our cases, first of all, the first lemma, the way in which we prove this is very similar to the idea of Golan, Gelander, and Terschenko. The difference is we already knew a lot about Thompson groups. So this lemma essentially came from a lot of corollaries and new proofs, but also a lot of lemmas and corollaries that we knew of. For example, they made use of revealing pairs from the paper Higher Dimensional Thompson Groups by Matthew Green, in which it is that section of the paper is essentially about dynamics of Thompson group V. We generalize this using forest file diagrams, which is essentially why I told you that much about forests, because they are less intuitive, but they can be useful, as they were in this case. So you are able to prove that these groups act in a certain manner just by looking at a certain kind of forest file diagram. The second part here, the corollary, it's the easiest part, definitely, but it's where you see how we use the weak cell transitivity. And I think it's also where you see why this works for normal subgroups. We are just conjugating, so this definitely has to work for normal subgroups, sorry. And the last part, we just needed to, this is the most technical part. We essentially need to choose the proper subsets and then essentially the proper elements in the conjugacy class of each, on each conjugacy class. And you end up with this. Now, I'm 5 minutes, and maybe I'm going to finish like 1 or 2 minutes earlier, but as you can probably tell, there is a lot to study about these groups. So these are just a few questions that I think should be answered about them, but there are definitely many more. One of them is very hard to ignore, because every rearrangement group that I described so far has simple commutator subgroup in one way or the other. No, this is not always true. We know rearrangement groups, especially in particular Higman-Thompson groups, that are another kind of generalization of Thompson groups that are contained in this family, whose commutator subgroup is not simple. You have to go down to the second commutator subgroup for them. But we don't then know, maybe we can prove something about the second commutator subgroup of everyone, of every rearrangement group, or maybe we just need to find the right family of these groups. But there must be some sort of more general result, because it's really turning out to be everywhere, the result, right?
I don't know if I understood, but do you say that maybe if you take second commutator group, maybe you can expect for all rearrangement groups which is simple?
That would be amazing. Yeah, that would be.
But you don't have counterexamples.
Sorry?
You don't have counterexamples, and you ask.
Right now, I mean, there are a few kind of silly arrangement groups, like finite cyclic groups can be built here. But if you exclude, and also trivial rearrangement groups can be built from non-trivial replacement systems. But I think that if you exclude a few almost trivial rearrangement groups, that could be one thing that could be proven, maybe, that the second commutator subgroup is simple. I mean, I don't know if this is true, but I cannot think of any counterexample right now.
And speaking just about the first commutator group, do you have some sufficient conditions so that both TA and TB will fit in? So far you mentioned that in the case of TA and TB, right? So the first commutator group is simple. Yeah. Do you have a more general result? Do you have a sufficient condition for rearrangement groups?
Not
specifically for bicyclic and airplane. Do you have some general condition?
No, and that is kind of what I think we should try to prove. And yeah, exactly. I'd like to have either a result about every rearrangement group, but that would be maybe too much.
No, but for the first rearrangement group, you said you have counterexamples, right? It's not always simple.
Exactly. Yeah, we have.
I think is it possible to have some sufficient conditions so that the first commutator group is simple?
Yeah, as I said, I don't know if it's possible, but that is kind of what I think we should try to look for. This is kind of what I mean with class of the arrangement group here. Maybe it's possible to find some sufficient condition, by which I mean a class of these groups for which we know that we can prove that the commutator subgroup is simple.
So your proofs are kind of by hand then?
And for TB and for TA, yes, kind of. As I said, it's because we know that much about commutator subgroup that we didn't even need to really go very general. But yeah, this is kind of what I'm working on right now, and I really hope that we can do something about this. Yeah, by maybe finding a class of groups, or maybe proving something going down to the second commutator subgroup. Now, another thing that I think is interesting is that we know of we exactly know many generating sets for these groups, like the one for TA, TB, Thompson groups, and so on. So maybe we can even find an algorithm that, given a replacement system, gives us a generating set. I don't know, but that would be amazing. But of course, we definitely need the proper hypothesis here, because we know of rearrangement groups that are not finely generated. So we really need to be wary here. But yeah, this is something else I think is worth looking into. And not only finite generation and generation in general, but also finally finite presentability and all of the other finite properties. So we know of a sufficient condition for a group to be F-infinite, which is good. Maybe we can find different conditions, and maybe we can find conditions for just finite presentability, for example. And as a last thing here, we don't really even know how these groups interact with each other. Like if you have two replacement systems, you have no idea to tell if the rearrangement groups are going to be the same isomorphic, or maybe one the subgroup of the other. It would be great, for example, just as an example, to have two replacement systems that are the same up to either adding an edge, maybe gluing two vertices, or modifying the replacement systems in some simple way, and then having the rearrangement groups being like one the quotient of the other, one the subgroup of the other. We don't know. And I think this would actually shed a lot of light on how these behave. And also, maybe if two replacement systems are similar, we would like to say that the groups are isomorphic. We don't have anything like that so far. And yeah, okay. This is everything I wanted to tell you. So thank you very much for your attention.
Do you know about commutator width? So like F, you know, it's 2 ends, but so like any element in the commutator subgroup is a product of at most 2 commutators for F.
Okay, yeah.
Do you know if that might be?
I have no idea. I don't think this has been investigated for PD and TA, and so yeah. Yeah, and I cannot think of an example right now of any commutator element that is that has longer length than 2.
Consider basilica group. Is it correct that it is a subgroup of transformations of non-locally finite bracket string?
Non-locally finite
Bracket string. Bracket string.
Yeah, the Verhofstadt tree.
I don't.
It seems that there is tree structure.
Yeah, there is for the Basilica Thompson group, which is not. Unfortunately, there is this naming issue. It's not the Basilica group because I think that is another group. The Basilica Thompson group has this basic structure.
Group which is related. Yes,
Yeah.
but
This is the tree structure. Essentially, you start from 4 branches or roots, and you go down by splitting in 3. Yeah, so the triadic structure.
so it is contains in automorphisms of some bracket string.
It's like Thompson groups. You are.
No, for Thompson groups you have pattern, but here we have automorphism, no?
No, I'd say these are the same as Thompson groups.
Yes.
This is actually, if you completely forget about the labels, this is actually a Thompson group. So these work exactly like Thompson group. You are. This is only you only consider a bijection on the labels.
But these pictures, well, no.
Wait. Maybe this one is better.
You call this, yes, this picture.
Yeah, this happened to be you're right. This is not the best example. This happens to be regarded as an automorphism, but you can actually take different examples. Wait, I'm going to go to here so that I can write an example. You can actually take examples in which you do something like this. I'm going to forget mostly about the other. For example, like this, and you map the leaves of these 2 trees, one to the other. So this is not an automorphism.
But if we write circle, then it seems it must be automorphism, not? It acts by homomorphism with picture, and it must send one circle to another, tangent circle to tangent circles, no?
Yeah.
So it seems it preserves structure of tree.
And the thing is, this tree structure is not being preserved, this one, because the levels of this tree are actually just a number of replacements that you needed to do to be able to access an edge of the graph. And you don't need to preserve this in general. For example, you can take an expansion of this graph where you have a very, very tiny loop here, which means that it's very low on the tree. And you can actually map it all the way to a very big loop, which means that you are mapping it up on the tree.
But structures of tree is preserved, it seems to me. It is homeomorphism of space which was drawn. And space which was drawn has some structure of T.
I'd say, as far as I know, the structure of the space that I drew, which is the limit space, the Basilica limit space, can be regarded as a quotient of the boundary of the tree. That is the structure being preserved, technically. Because if you take the boundary of this tree, this is a counter set, a counter space.
Yes, but in Basilica space, you have circles.
Yeah, by circles, you mean the loops.
Loops,
Yeah.
yes. And set of loops have structure of tree.
Sorry, I think I understood what you mean. Yeah, because which is not true in the airplane. Yeah. Because
Yes, not to S for airplane.
yeah, you have essentially this sort of adjacency between loops. Yeah. I think you can use this to put these inside an automorphism of the group. I mean, the tree would be these, which I'm doing very badly, but I mean it is this guy here.
And
The issue,
set of edges is cyclically ordered.
but this is not locally finite though.
Yes, yes, of course, not locally finite, yes. But it seems it is
Okay,
interesting structure.
sorry, yeah,
And
Yeah.
is it correct that this group is dense and due to homeomorphism of high space,
Yeah.
or whole space or not?
I don't know, I never actually studied this under this aspect. Yeah, I don't know, that's an interesting question. Yeah, thank you.
Thank you. And I have one small question. Several times you told that group is as F infinity. What
Yeah.
this means?
It's finiteness property, like it's actually a strong generalization of being finely presented. You have one for each natural number n. It admits a classifying space that with a finite amount of cells that vanishes like, after n.
Okay. Finally presented with finite CCs.
Yeah.
Okay.
Just a basic question. Does the Thompson group, does F have three sub-semi-groups?
Three sub-semigroups. I don't know.
I think the answer is yes. Yes, for that.
Yeah, I was wondering if maybe there's some way to see from the rearrangement.
Oh, yeah, right. It's an H&N extension of itself.
Oh, right.
Yeah.
I didn't even know about it.
Yeah.
Yeah. Right. Thank you very much.
Yes, exactly.
How many minutes we got?
8 minutes.